Understanding physics, hard bits, and this one is about nuclear binding energy. What's that then? Well, let's talk a little bit about the strong nuclear force. Now, the strong nuclear force, look at the graph. It has a very short range. It's only at the most 3 femtometers, yeah? 2.5 femtometers, very short range. It is very strong. Hence the name, the strong nuclear force. It acts on protons and neutrons. It acts on things which have quarks in them. Yes, very strong. It's like the glue which holds the nucleus together. Yes, the exchange particle is the gluon. Yeah, it glues the nucleus together. I think of it as Velcro. If you imagine magnets repelling each other, which are held together by Velcro, so it has a very short range. These particles are almost touching each other, yes, and it holds protons and neutrons together. The neutrons do a very important job, yeah, they provide superglue. They help to hold the nucleus together. Now, this carbon nucleus is held together by the strong nuclear force. And if we wanted to pull it apart, to pull it into its constituent particles, yeah, 6 protons and 6 neutrons, we would have to do a lot of work. Yeah, why? Because we'd have to pull this Velcro away from each other. We would have to do an awful lot of work to pull it to pieces. Yes, to go from the carbon nucleus to the particles on their own with nothing to do with each other, we would have to do an awful lot of work. So in the nucleus, these particles have got negative potential energy. They are in a potential well, yeah? And the total amount of energy that they have, the amount of work that we would do to get from left to right, is the binding energy of the nucleus. Now, this isn't an amount of energy that the nucleus has. It's the opposite. It's how much work we would have to do to pull it apart. So if you like, these particles have got negative potential energy, and it's the total negative potential energy. It's a little bit like if you were in prison and the bail was £10,000. Does that mean the prisoner has got £10,000? No, it means that if somebody gave him £10,000, then he could get out of prison. It's a negative quantity. It's the binding energy of the nucleus. It's negative potential energy. Here you go, look at this. These guys at the bottom of the well, they're inside the nucleus and they can't escape. They need energy to get out of the potential well. The 2 guys at the top, they have no potential energy, 0 potential energy. They can go off and have adventures and solve crimes and things. They can do what they like. Yeah, the guys at the bottom can't escape. They need energy to escape. The total amount of energy is the binding energy of the nucleus. Now, this is crazy. Because this system has more energy, the particles on their own, it has a bigger mass. If you've got 2 systems and one of the systems has got more energy than the other, you know, and they're identical in every other way, then it has a bigger mass. A stretched rubber band has a bigger mass than a floppy rubber band. A car whizzing down the motorway has a bigger mass than a car not moving. Yeah, a hot cup of tea has a bigger mass than a cold cup of tea if everything else is identical. Why? Because that system has got more energy. And I am sure you will have heard of an equation, E equals mc squared. If you know the difference in energy, you can work out the difference in mass. And for something like a rubber band, it would be a tiny, 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 very tiny. You wouldn't be able to measure it, yeah, a billionth of a gram. However, because these particles, because the amount of energy is so big, compared with the mass of the particles, you can actually measure the difference in mass. And this is how we can work out the binding energy. If we can measure the difference in mass between the nucleus and all of the bits, or between the atom and all of the bits, we can work out the binding energy. Look at this. So the mass of a carbon atom is 12U. By definition, the mass of a carbon 12 atom is 12 atomic mass units. The total mass of all the bits, including the electrons, is 12.09894 atomic mass units. Notice there is a measurable difference. I've included the electrons because the 12U is the mass of the atom, and that includes the electrons. The binding energy is nearly all of it nuclear. Less than 0.1% is going to be like, to take away the electrons. The energy needed to take the electrons will be tiny in comparison. Okay? The important point here is the difference in mass between the nucleus and the bits. In any questions, now 1 atomic mass unit is 1.66 times 10 to the minus 27 kilograms. You'd be given that. You'd use E equals mc squared to calculate the binding energy in joules, and then maybe change that to mega electron volts. There is a little shortcut which you may be given. This 1 atomic mass unit is 931 mega electron volts. That's very, very useful. So our carbon 12 atom, we worked out the difference in mass. So the binding energy of the atom, which is nearly all of that, is the binding energy of the nucleus, 92.1 mega electron volts. Yeah, or minus 92.1 mega electron volts for reasons discussed earlier. Look at this equation. Do you recognize it? You've got a uranium-235. It absorbs a neutron, becomes very, very unstable. Then it splits into 2 bits. In this case, the krypton-92, the barium-141. You also get 3 neutrons. They may go off and cause a chain reaction. And then you've got energy as well. Okay. Now the energy released will be the difference in the total binding energy. Going from there to there, the binding energy will increase. And because the binding energy increases, energy is released. Yes? Because these particles on the right here, these particles are in deeper potential wells. Yeah? The total binding energy increases, therefore energy is released. In an exam question, you'll be given the mass of the nuclei, so you don't have to worry about the electrons. You might be given the mass in kilograms, or you might be given it in atomic mass units, and then convert it to kilograms, or just use my little shortcut. Depends. I've seen a variety of questions. Looking at this is my model. Okay, so the uranium-235 is 235 guys at the bottom of this well, yeah, whereas over here we have 92 guys at the bottom of that well, 141 guys at the bottom of that well. Notice that the wells are deeper, and the wells are deeper because the average binding energy per nucleon is greater. Yes, the average binding energy per nucleon is greater. Those wells are deeper. Energy is released because the total binding energy increases, and this is because the binding energy per nucleon is greater for those nuclei. This graph, you must know this graph. This is a graph of the binding energy per nucleon against nucleon number. Looking at the graph, looking on the x-axis, you've got your small nuclei. There, you've got your medium-sized nuclei there, and you've got your large nuclei, your big fat boys over there. And the point is, in nuclear fission, your uranium-235 is going to split, and it's going to work its way from right to left on this graph. How does this graph show that nuclear fission is energetically viable? What does that mean? How does this graph show that energy is released in nuclear fission? And the answer is because the average binding energy per nucleon of the fission fragments is greater. This means that the total binding energy increases. This means that energy would be released. Okay, if your uranium-235 splits into that and that, yeah, because these two are higher up the graph than the uranium, yeah, they have a bigger average binding energy per nucleon. That means that the total binding energy is bigger. That means that energy is released. If you understood that, then this question will be a piece of cake. Have a go at it on your own. So from the graph, find the binding energy per nucleon of each of the nuclei involved. So that's helium-2 is there, that's deuterium. Yeah, what's that, about 1.1? Helium-3, that's tritium, is there. Yeah, what's that, about 2.8? Yeah, so 1.1 times 2, and then 2.8 times 3, and that'll tell you the total binding energy there. The binding energy of the helium-42 will be bigger. There it is up there, it's about 7.1. Yeah, so the total binding energy is bigger. Don't worry about the neutron, doesn't have any binding energy. And so the difference in binding energy is the energy released. And if you worked it out properly, you should get about 17.6 mega electron volts.